Okay, so we are going to rationalize this complex number. We can't have an I in the denominator. Why? It's the square root of -1. I is the square root of -1, and you can't have a square root in the denominator and be simplified. So how can we get rid of the i's? We saw in our Bell work that you can multiply by the complex conjugate and get a real number. So that's what we're going to do. We're going to multiply this denominator by its complex conjugate. 5 plus 2i. Now, if you do that in the denominator, you have to do the same thing in the numerator. That way you're not changing the value of this expression. It's like you're multiplying by 1. 5 plus 2i over 5 plus 2i is 1. So we just multiplied by the complex conjugate of the denominator. And now you just FOIL it out. That's going to be 10 plus 4i plus 15i plus 6i squared. Don't forget, one of the common mistakes that people make is they forget 3i times 2i is 6i squared. A lot of people will forget and put I, but I times I is I squared. And then we FOIL the denominator. 5 times 5 is 25. What happens to outer and inner when you multiply by the complex conjugate? They cancel out, just like in our Bell work. So I don't even have to do my outer and my inner because they're going to cancel out. And so I just do last times last, and that's minus 4i squared. So on the denominator, you really just have to do first times first, and then last times last. That last times last is going to have a minus I squared, minus something I squared. Any questions so far? Now we have some simplifying that we can do. 6i squared is equivalent to what? -6. Anytime you see an I squared, that's a -1. So that's going to make that a -6. And then minus 4i squared will be plus 4. And we just simplify. In the numerator, we end up with 10 and -6 as our real parts. So add those together, you get 4. You end up with 4 and 15i as your imaginary parts. So you add those. And then your denominator is 29. Now, most textbooks will split this up into 4 over 29 plus 19 over 29i, so that you have the form a plus bi, where a is the real part and b is the imaginary part. Any questions? All right, so y'all work this one out. I'm going to run through it very quickly. We multiply by the complex conjugate of the denominator. In the numerator, that gives us -3 plus 3i minus 2i plus 2i squared. A lot of you missed the negative times a negative is a positive. Then we have in the denominator first times first and then last times last. We can change those I squareds to -1s, so that'll make that a -2. 1 minus -1, so we have a +1. In the numerator, we combine the real parts. -3 and -2 gives us -5. 3i minus 2i is just +1i, and our denominator is 2. When we split that up, we get -5 over 2 plus 1/2i. If you write it like this, it's in the form a plus bi. Now, if you didn't write it like that, it's not necessarily wrong, but you don't have it in the form a plus bi. So if you're asked to write it in the form a plus bi, you need to split it up into -5/2 plus 1/2i. Any questions? Graphing complex numbers, it's very similar to graphing ordered pairs. You're going to graph the real part on the x-axis and the imaginary part on the y-axis to come up with what resembles an ordered pair. So for 2 plus 3i, the real part is 2 and the imaginary part is positive 3. So you'll go to 2 on the real axis and 3 on the imaginary axis. Where they meet, that's your 2 plus 3i. So B, negative 3 plus I. We'll go to negative 3 on the real axis and positive 1 on the imaginary axis. Where they meet, that's our B. See if you can do C and D. All right, I hope that you did 4 on the real axis and negative 3 on the imaginary for C. What about D? How'd you do D? What's the real part? The real part is 0. So we just go down to negative 2 on the imaginary axis. Are there any questions? Y'all like this? Thumbs up, sideways down? Thumb gauge. Okay. Next thing we're going to do is we're going to find the absolute value of 2 plus 3i. Okay? So I want you to find the absolute value. Should have written this in black. Oh well. Find the absolute value. And we're just going to do it for A. 2 plus 3i. We can do this with the definition of absolute value. What is the definition of absolute value? It's not the magic bars that make everything positive. CJ? How far a number is from 0. So if we're doing A, and we see how far it is from 0. See that blue line right there? That's how far it is from 0. I can find the distance between those 2 points. Do y'all remember the distance formula?
I remember doing it.
Okay. D equals RT, but that doesn't help us here when we have 2 ordered pairs. You can use the distance formula. D equals the square root of the difference of the x's squared plus the difference of the y's squared. X1 minus x2 squared plus y1 minus y2 squared. Or, does anybody see another way to find that? Does anybody notice a triangle? Pythagorean theorem. Very good. We can make a triangle out of this. Okay, if we want to know this length, what part of the triangle is this? This is our hypotenuse, so it would be the C. This would be our little right angle. This is 2. This is 3. 2, 3. See that connection? So we would say that our distance, or our absolute value of this, is 2 squared plus 3 squared equals x squared. 2 squared plus 3 squared equals x squared. So that's going to be 4 plus 9, which is 13. And then how will we solve for x? The square root. And so our absolute value of 2 plus 3i is equal to the square root of 13. Why do I not need the plus minus here? I'm taking the square root of x squared. Why don't I need the plus minus? Okay, it does have to be positive, but why does it have to be positive? You can't have a negative distance. Back to the definition. Absolute value is the distance from 0, and you don't have negative distance. All right, y'all want to try B? Whether you do or not, you get to. Oh, wait, before we do that, in general, the absolute value of a plus bi is equal to the square root of a squared plus b squared. And we showed that with the graph. So I want y'all to try b. Find the absolute value of b. People on the video, the answer is the square root of 10. All right, now we're going to look at powers of I, and I'm going to do two different methods, but it's important to know that I is not simplified if it has an exponent. These are the two powers of I that we know. We know that I to the first power is I, and I to the second power is -1. So our first method is going to be using just those two powers. You don't have to memorize anything else. And here's what you do. Say we have I to the 14th. We are going to rewrite that using I squared and I, if we need I. Okay? So we can rewrite I to the 14th as I squared raised to what power? The 7th. Because we know that when you raise a power to a power, you multiply. So I squared raised to the 7th. Basically, you just divide this number by 2. What is I squared? -1. So we have -1 to the 7th, which is -1. Simple enough, right? Let's look at a different example that has an odd exponent. I to the 23rd. Now, if we're going to be using I squared, that's only going to give us an even number. When we raise 2 to another power and multiply, you're only going to get even numbers. So what's the next closest even number below 23? 22. So that would be I squared to the 11th. And then how many more i's do we need? One more. That gives us 2 times 11, which is 22. We need one more to give us 23. So you have -1, I squared is -1 to the 11th times I. What's -1 to the 11th? -1 times I is -I. You can also get a +1 or a positive I. How do y'all feel about this method? Okay. Let you do one by yourselves. How about you try I to the 13th. I to the 13th. Try this one by yourself. The answer is I. Our second method relies on the fact that the powers of I repeat every fourth exponent. So I to the first is I squared is -I. We found that I to the third is -I, and that I to the fourth is +1. So they repeat in this pattern, I1, negatives in the middle. So to use this method, you're going to have to memorize I to the third and I to the fourth. Okay, you're going to have to memorize what those two are or figure them out on your paper before you start using this method. But this is what you do in method 2. You divide by 4, and the remainder tells you the power of I. Divide by 4, and the remainder is going to tell you the power of I. So like if I had I to the 22nd. I to the 22nd. I would do 22 divided by 4. 4 goes into 22 5 times with a remainder of 2. So I'm interested in the remainder. The remainder is 2. And the remainder tells me the power of I. So it's the same as I squared, which is negative 1. So I to the 22 is negative 1. I to the 1,081. I to the 1,081. Well, I can divide 1,081 by 4. And I have a remainder of 1. So that tells me that this is the same as I to the 1, which is I. So this is method 2. You divide by 4 and you look at the remainder. Now, the reason this works, going back up to the easier one, the smaller numbers, I to the 22. We can rewrite I to the 22 as I to the 4th raised to the 5th power, since 4 goes into 25 times I squared. I to the 4th is 1, and 1 raised to any power is 1, so that would be 1 times I squared, which is negative 1. That's why the dividing by 4 works, because any power of I to the 4th is going to be 1. So that's why you only have to look at the remainder. Any questions on this method? I did want to point out, on method 2, on this method, if you're using your calculator to divide, you're not going to get remainders, you're going to get decimals. So if you're dividing by 4 and you get a remainder of 1, 1/4, a remainder of 1 when you divide by 4, is the same as what decimal? 0.25. So if you get a remainder of 0.25, that's the same as I to the 1. So what would be a remainder when you get 2 when you're dividing by 4? 0.5. And so 3 would be 0.75. And if you don't get a remainder, that means it was divided evenly by 4. It was divisible by 4. So the answer is 1. So that's a shortcut. You can just take the exponent, type it into your calculator, divide by 4, and whatever the remainder is, that tells you if it's I, -1, I, or 1. Okay?